Hello, my name is Victoria Gamdoller, and this is High-Level Synthesis Optimizations. So first, I have my Bash code and my Python code. My Bash code is each individual run, which, what am I talking about by individual runs? So I have a lib_sobel.info file, which lists each possible attribute 1, 2, 3, 4, 5, and all of the possible variables that they can be, such as unrolling a for loop, all or 0, and then attribute 1 can be RAM, register, or expand, and then attribute 2 can also be ROM or logic, and then attribute 3 has the same options as attribute 2. This is the flib and blib files that the bash code will call. So for each individual run of a C code, we run cpars and bdltran, which is shown here. So cpars and then bdltran with the flib and blib files. And collect data is my data collection of all of these enumeration of the attribute files. So first I get all attribute combinations from the lib_sobel.info file. And then I write each combination to the adders all file, which is right here. And this just lists all combinations that the attributes can be, up to 192 combinations. And then it also, each iteration, because it's for combination in combination, so it's each combination, it is changing this adders.h file to be the current combination of attributes, so define attribute, and then which specifications, and then for the C file, just to show you where all of the attributes are, attribute 1 is here as a char array, and then attribute 2 and 3 are these 2D arrays, and then 4 and 5 are for loops, as seen in the sobel.c file. Alright, and then next, so the attribute was changed, and then it was copied from this location into the output folder, which all benchmarks data, so sobel's benchmark data, 1.h, so attribute.h, the integer.h, just to copy it to the file. And then we have the bash run path. We call the bash file, run it, and then create the current iteration of the path directory, so make directory, and then copy the QOR and CSV files into this directory here. And so that is what the data collection does. I would run it as Python, however, it takes a bit of time, so I'm not going to run it this time. However, I am going to run my find pair optimal values file. So find pair optimal values. So what this does, now that the data is collected, it parses all of the attributes and sees all of the attribute combinations and creates a data frame. It also extracts the second line of the CSV files. So here you can see that the area for this first iteration is 343 and the latency is 18. So it would extract those numbers from each of the 192 files. So you can see here. And then scrolling down, it prepares the data, so it makes it into a data frame of the paths and CSV data. And then I was also sometimes working with older Python versions, so I had to flatten certain arrays, and then find para-optimal values. So when I have my data frame, I pass it to this function, and it finds the indexes of all my para-optimal values. And then once I have the indexes of my para-optimal values, so what para-optimal means is that for this, you want the lowest area and latency of a design, and if there's a trade-off of one has a lower latency but a higher area, well, you would also take that design because you want the lowest latencies and the lowest areas. However, if one design has both the lowest area and latency, then you only have 1 point, which we will see with Sobel. And then this just gets the area and latency point values for the find para-optimal array function. Let me see. Okay. And then this is just calling all of those functions. And then this is me printing these results so I can store it in the output text file here. And then I graph the area and latency to a MATLAB graph, MATLAB plot, and let me show you this working. So I'm going to remove the output file, and yes, and then calling this function, and in a moment. Okay, so you see, as I said before with this graph, there's only one para-optimal point. Now, that being said, there's only one area and latency that has the para-optimal value. However, there are multiple designs that lead to this area and latency. So latency of 1, and looking at the output file, oh, this needs to finish. So closing this so that this can finish. Okay. And we see at this end of the file that there's only one area and latency, so area 175, latency 1, that lead to the best para-optimal values. But you can see like there's many designs that were generated, but specifically looking at the table of all of these designs is here. So I use the output file and put this into a table. So attribute 1 consistently has CyberArray expand and array index constant. So attribute 1's array is expanded. Now the for loops are also unrolled times all, so they're fully unrolled. However, attribute 2 and 3 have variants on register, ROM, logic, expand, so forth. So things to take a note that attribute 2 and 3 didn't seem to impact the area and latency as much. Just something to take a note. And so just possible reasons of why there was only 1 point. I'm going to run it again so we can look at the graph. So possibly why there was only one para-optimal point of area and latency is that as you increase the latency, as you increase the clock cycles needed for a design, the area to compensate for storing the value and then loading that value for the next clock cycle could have additional area that's generated. So therefore, that is one reason why increasing the latency sometimes can lead to larger designs. So that is a possible reason of why the area and latency, there's only one point for the para-optimal value, so the optimal value. So that is the looking at all of the attribute combinations of sobel.c. Thank you and have a good day.